In this worked example, I'm going to be looking at a question from the May-June 2018 paper 21 for AICE Physics 9702. This question reads, for a progressive wave, state what is meant by 1. The period. The period of a wave is the time that it takes that wave to propagate. And so I would state for the period the time in seconds per wave. The time in seconds per wave, for one oscillation, for one complete oscillation. State what is meant by the wavelength. Well, that's going to be the distance. I'm just going to keep it simple and say the distance from crest to crest. So the crest of the wave, like you can kind of see down here, to the next identical point would also be a crest, but really the wavelength is the distance from sort of any point to the next exactly identical point. So if we look at like kind of the wave here begins here and then it repeats right there, and so the wavelength here would be the distance from this point to this point, or the distance from crest to crest, or from trough to trough. You can kind of think about the wavelength any one of those. The question goes on to give us this figure. It says figure 4.1 shows the variation with time t of the displacement x of two progressive waves p and q passing the same point. And it says the speed of the waves is 20 centimeters per second. We are to calculate the wavelength of the waves. It's important to note here that to always be mindful of what's being plotted on the x-axis, and so here we can see that it's time measured in seconds, and so by looking at sort of how much space the wave occupies, we're really looking at how much time it takes, per wave. That, as we've said earlier, is the period. So we have to kind of, coupled with this information, the speed of the wave, we got some information here where we can read off the period of the wave, we should be able to calculate the wavelength. The first thing that I would do is kind of look and see that the wave period looks to be 0.6 seconds, and so we can say here, if we're looking at, for example, wave P, pretty evenly crosses there, and so the period of wave P is equal to 0.6 seconds. So we can calculate the frequency with the equation 1 over t, and so 1 over 0.6 is equal to 1 over 0.6. You can see there you got 1.6 repeating, so that is 1.7 hertz as the frequency. And if we know the speed of the wave, that's the velocity. The equation is speed or wave velocity equals wavelength times frequency. Now that we know the frequency, we were given the speed of the wave, we can deduce the wavelength using this equation. So I'm going to rewrite the equation down here with wavelength being the subject. So velocity is equal to wavelength times frequency, then wavelength is going to be the velocity divided by the frequency. Now here they want the wavelength in centimeters. Now I'm given the speed in centimeters per second, and so if we're mindful of that, we can just leave that 20 centimeters per second divided by, now the frequency here, 1.66, repeating. Reciprocal seconds is the same thing as hertz, and so those units are going to cancel. We're left with centimeters, and so our calculation becomes 20 divided by 1.66666. 6 repeating, we get 12. So the wavelength must be 12 centimeters. The question goes on to ask us to determine the phase difference between the two waves. Now phase difference is sort of like how much is one wave off from the next one there. If we look at wave P here, we can see that it's got this period of 0.6 seconds. It kind of begins right here, right? Well, it looks like wave Q down here doesn't really, start until 0.2 seconds, right? So it's sort of shifted off by 0.2 of the entire wavelength. And so one way to calculate this, the phase difference between the two waves, is to kind of think about wave Q being shifted 0.2 seconds out of the total 0.6 seconds of wavelength. This is like, you know, by how much is it off? If they were perfectly lined up, the phase difference would be 0 degrees. So you kind of have to look at how much it's shifted over there. So 0.33333 times, they want in degrees, so there's 360 degrees in one cycle there. So that gives us a phase difference of 120 degrees, right? It's off by a third, you know, 120 out of 360. That's a way to think about that. To calculate the ratio of the intensity of the waves, we're going to have to look at some information on the figure, which is the amplitude. And so the amplitude of wave Q is 3 millimeters. The amplitude of wave Q here is 2 millimeters. The amplitude is the distance from equilibrium, 0 millimeters of displacement, up to the maximum displacement. So we can say for wave Q, there is amplitude equal to 2 millimeters. That's for wave Q. We can say that the amplitude of wave P is 3 millimeters, and then intensity is proportional to amplitude squared. And so to get the ratio of these amplitudes, we're going to look at the ratio of the ratio of the intensities rather is going to be the ratio of their amplitude squared. And so we can think about it as 2 millimeters squared over 3 millimeters squared. That entire quantity is squared. So we have 2 squared over 3 squared. The units millimeters are going to cancel, and we get 0.44 is the ratio of intensities. Again, the key idea there is that intensity is proportional to amplitude squared, and amplitude is the maximum displacement, which we can read off the graph. It says the two waves superpose as they pass the same point. Use figure 4.1 to determine the resultant displacement at time t equals 0.45 seconds. At t equals 0.45 seconds, it looks like, well, this is 0.5 seconds, and so 0.42, 0.44, 46, 48. So every square here is 0.02 seconds, and so 0.42, 0.44, 0.45 would be right here. And we can read off the displacement of wave Q is 1 millimeter there. And also at that time, we can see that the displacement of wave P is down here at -3. And so we use the principle of superposition, which just states that the algebraic sum of the displacements of the two waves is the resultant displacement of the new wave. And so we're adding 1 millimeter to -3 millimeters for a total displacement of -2 millimeters. Well, the millimeters are there. So that is a good worked example for introducing wave physics.